For the third part of the talk, I discuss the subquantum theory in more detail, which depends upon the non-hermitian states. In terms of Pauli spin matrices, these non-hermitian building blocks show two angular momentum and a phase. This is now fundamentally different from quantum mechanics. The quantity S is the state of one ontic particle. It does not obey quantum mechanics because it is non-hermitian. This is the definition. Unless it gives the right answers, it should be thrown out. In fact, it gives the right answers, and using this, as I will show, resolves all the questions raised by EPR, gives a totally different view of a free particle with spin, and accounts not only for quantum mechanics, but also for the anomalies. Let us compare the quantum Hermitian state with this subquantum particle. In quantum mechanics, the statistical or density operator has two pure states of +1 and -1. The non-Hermitian form relates to a single particle, not an ensemble. That is a major difference. Now, the statistical density operator was first introduced by John von Neumann in 1934, and for spins, the form given describes a pure state, one lying parallel to the external polarizer, which is oriented in the z direction, and the other one anti-parallel. Note the presence of this term, which is missing in quantum mechanics. It accounts for the coherence, but it is very different from the coherence of quantum mechanics. This coherence is between eigenstates. However, eigenstates are orthogonal, and therefore there is no coherence between them from quantum theory. The situation is different for non-Hermitian operators that can have non-orthogonal eigenstates. Another difference is that quantum mechanics gives the quantum state as polarized in the laboratory z direction, as I mentioned. In contrast, an isolated subquantum particle is oriented in its own body-fixed frame of reference, called the spin microframe. Every subquantum particle is in general oriented differently, and each spin microframe can be rotated to the laboratory frame. I told you subquantum theory is different from quantum mechanics. There is more. The subquantum spin has internal structure. Quantum mechanics does not predict any structure. It treats the spin as a point particle. However, subquantum spins have two orthogonal axes of spin quantization, one determined by the z component of the Pauli spin matrix and the other by the x component. The structure is therefore two-dimensional, with one magnetic moment pointing along the microframe z-axis and the other along the x-axis. The last term is not angular momentum, but rather it is a rotation operator. As such, it orients the 2D structure of a spin in three-dimensional space by the commutation relations. This is another major difference. Whereas in quantum mechanics, the commutation relations lead to the Heisenberg uncertainty relations, which show dispersion, in the subquantum theory, the non-commutation does just the opposite. It orients the two-dimensional particle exactly and specifies it completely with no dispersion, much like a vector cross product orients two vectors in three-dimensional space. Now, I have mentioned that the subquantum mechanics is beyond measurement. So let us go to the limit and assume that in the briefest instant of time we can freeze a subquantum particle. In this limit, it looks like a two-dimensional particle. Finally, it is assumed a magnetic moment lies along both axes of quantization. Without this structure, agreement with experiment is not possible. Finally, symmetry breaking leads to degeneracy. Once again, this is one spin from an ensemble of many, each oriented in its own microframe. Within a microframe, each spin can be oriented in four ways. In fact, these are resonant structures, with the eigenvalues being identical and the wave functions differing by a sign only. These are degenerate orientations of a two-dimensional spin. The integers simply define the different octants of the microframe. The integers are hidden variables. Now these extra hidden variables cannot be seen in the presence of a probe. If we take our 2D spin and place it in a magnetic field, one axis of quantization lines up and the other processes so fast that it randomizes the other degrees of freedom to give us the usual spin of quantum mechanics. Unless subquantum theories predict something new, they are simply interesting exercises. In addition to the ensemble view, there are two major consequences of the subquantum theory. The first is that a new spin state is predicted. If a spin is completely isolated, our usual notion is that it retains its spin vector property.